the two database backends in some ratio. I'll also use my pointer. Okay. As another example, there can be a security policy where beta allowed to use the post storage service directly. So we might want to enforce that policy. As another example, we might need to collect fine-grained metrics. As an example, the requests that are coming into the front end, we want to check how many of those failed with an error code of 500. All of these policies can, in principle, be implemented inside of the applications themselves. So, for example, these security and traffic management policies can be written by the developers inside the code of post storage. But that complicates development, deployment, and configuration. Each time a policy is changed, you will need to go and change the application code and redeploy all of the application instances. And that is not desirable, and therefore there is a need to do something more. And that's why people came up with service meshes. What happens in the service mesh architecture is that just below the application layer, there is another infrastructure layer called the service mesh, which basically consists of sidecars. Each sidecar can be thought of as a container, which runs alongside the application containers. And all of these policies are enforced in these containers. The way these sidecars work is by intercepting all incoming and outgoing traffic. So any request which goes into the post storage service would be intercepted by its attached sidecar. This sidecar will parse the layer 7 request and then enforce the policy. So why is it required to parse layer 7 payloads? Is because these policies are required to be enforced over information that can only be, which is embedded deep into the payload. So for example, for a beta user, the sidecar will need to parse the payload, identify the right header which states what type of a user this is, check whether that is in beta, and then we can move on with the processing. So this is how service meshes came into being, and now there are like a bunch of service mesh offerings, as was also mentioned in one of the talks yesterday, I guess. So now let's look at how a developer or a programmer can actually provide these policies to the service mesh framework. So to give a very concrete and simple example, here is a microservice application which has a front-end service which talks to the back-end service. The back-end can in turn talk to database service which has two versions, and simultaneously there is some internal service which is used for maintaining the databases. And let's say we want to enforce the policy which says distribute requests from the front end to these two versions of the database in some ratio. In this case, it's a 50-50 ratio. Now, at the surface of it, it seems that this policy is very simple to implement. However, these data plane sidecars are not typically configured directly because there are so many of them. So what these service mesh frameworks have come up with is a control plane. And developers have to write policies that go into this control plane. Now here is the example of a policy of how this can be achieved. This policy, notice that each of these, this policy has a destination service. So when you are writing this policy, when the developer is writing this policy, they have to provide which destination service this policy applies to. In this case, because we want to, the target service in this policy is the database, therefore we need to specify that the host or the target destination for this policy is the service DB, the database service. And then we can have the actual logic where we say that how the traffic is to be divided. Now note that, and when this policy is submitted to the control plane can go ahead and enable these policies. And because only the backend and the internal services are talking to the database, these policies will come into effect at these services. However, note that our original policy was not to deal with, not to divide all traffic to the database service in this ratio, but only the one which is coming from the front end. And what we have written here is just for all the traffic. So we need something more over there. What that something more can be is that, let's say we have some way of providing an additional header in each of these requests. And let's say that header is called from FP, which stands for from front end. Now, how do we set this header? Is the following. The developer will have to write another policy which says that for all requests which are going into the backend service, add the header from FE. Now, this works because there is only the front-end service which is sending requests to the backend service. So now this policy can get enforced at the front-end service. And now it is complete. All the requests that go from the front-end to the backend get imposed by the policy P2, which adds a header on them. And then this backend service can enforce the policy by checking whether the outgoing request has the same header, and then we are good. Now this is the entire process, but it has three problems. First, the specific services are needed as policy handled. So we need to specify which destination service is needed for each of the policies. And as you can see, like when we had this path level policy, which spans multiple services, then we have to break down our policy into multiple smaller sub-policies. The second problem is that because the control plane does not know that which service can talk to which other service. So the graph I have shown here, the microservice graph, is the logical graph. By default, the control plane does not know whether the front end can directly talk to the database or not. So what it goes ahead with is it enforces all of the policies at all sidebars. But the point is that only some of them are actually enforced. So these shaded ones are the policies which are not really enforced, but they are still there either. And the third point is that there is this of the control plane, and all policies have to go through it. So the developer has only as much programmability as what the control plane can provide. And now, taking each of these 3 points, I'll explain why they are a drawback in current service mesh frameworks. So starting with the first one, what's the problem with having services as policy handlers? There are 2 problems. First, that it complicates policy specification. As we just saw, policies that span multiple services are needed to be broken down into per service policies. And for a microservice graph, which can scale to several hundreds of services, this can easily become a big challenge for the people implementing these policies. The second problem is that it requires that whenever the microservice graph changes, the policies are needed to be changed as well. These policies only work for the application graph for which the policies are made, and as soon as the graph changes, people have to go back and tweak the policies again, requiring manual changes. This makes the entire process annoying and cumbersome. And the root cause for this problem is that services are coarse-grained for policies that span multiple services. I'll come to our solution in a bit, but let's go through all of the problems first. The second drawback is that sidecars are needed at all services right now, because the control plane does not know which service can talk to which other service. And because these sidecars are running at all of these services, they impose overheads. They have latency overheads. So this is a quick experiment that we performed on 3 microservice benchmarks. And the red bar here is when we use, red and yellow bars are the ones when we use service meshes. So when we use mesh and we add these sidecars, it adds 2 hops for each request, one on the outgoing side and one on the incoming side. And therefore, it adds to the latencies. The second problem is that because these are continuously running, so they are continuously occupying CPU and memory resources. Again, the yellow and the red bars are when we have service meshes, and you can see that they are much higher than the case when we did not have them. And the root cause for this is that the control plane cannot make any optimizations. It is unaware of application tags. Moving on to the third drawback, there is the control plane in the middle. And the reason why there is this control plane is because sidecars have several layer 7, layer 4 filters, which are difficult to configure. Therefore, a control plane uplifts them and gives a higher level interface. And these control planes are typically developed by separate vendors than the actual data planes. So to give an example, the data plane is Envoy and the control plane is SDO. These are two different projects and therefore there is no real harmony. So the reason why this becomes challenging is, let's say I have two different data planes that I want to use. Then both of them will have two different vendors, control plane A and control plane B, and both will have their own programming API. So a programmer who wants to use both of these data planes will have to write two different programs for the exact same thing. And the challenge is that when a data plane evolves, so when Envoy is upgraded, then the control plane and its corresponding API also has to be upgraded. And what we found from some investigation of their GitHub repos, it seems that this process can take up to more than 4 months as well. And the root cause here is that there is no way for the data plane to uplift their abstractions to the developer. The only way for the developer to configure the data plane is via the control plane. So to solve these problems, we propose a principled redesign of the service mesh stack. I'll go over our key ideas in little detail. The overview is as follows. So the first problem was that services are not good and they are coarse-grained. So what we come up with is a new policy specification language called Copper that uses contexts as policy handlers. The second is that sidecars are overheads, and we realize that the control plane is in a unique place to optimize them. What this optimization is, I'll come to it in a while, but this part of our idea is called wire. And finally, there is a lack of data plane abstractions, and therefore we come up with a new abstraction which allows the data plane vendors to directly provide their functionalities to the policy writers, and we call this the abstract communication object, or ACO for short. Now I'll be talking about each of these three components one by one. So let's first start with abstract communication objects. What we mean by an ACO is any object that forms a semantic part of microservice communication. It's similar to how P4 came up with the mass action abstraction, and this abstraction allows for the data plane to express their functionalities. How it works is the following. Each data plane can provide a list of the abstract objects and the actions that it can use. Now these abstract objects are general enough. So to give an example, these objects can look like request, connection, and actions related to them. So a data plane can say that I understand what an HTTP request is, and I can perform actions such as set header, get header, and set get timer. And similarly, all data planes can do the same thing and uplift their functionalities in the form of these ACOs. For the developer, this is good because they get a common interface and they can write policies on generic ACOs instead of having to write it for each data plane separately. Therefore, they can use multiple data planes together. How the data plane provides these ACOs is in the form of something that we call spec programs for the specification of the data plane. This is basically a syntax for the data plane to say their functionalities. So here is an example of a very simple spec which says that the data plane supports RPC request, and it can perform actions such as get header, set header, and set deadline on this object. Now, any update in the data plane functionality can be directly used. Currently, what happens is that if the data plane gets upgraded, then a programming API has to be upgraded and the control plane also has to be upgraded. And this is challenging because the data plane and the control plane are different vendors. However, in our case, because the data plane is responsible for giving the ACOs or this spec, when the data plane is upgraded, the spec can directly be upgraded and it can be directly used by the programmer in their file. In the program. You can think of it as a header file. So when the functionality changes, the header file changes, and you directly get that in your program. You don't have to wait for the control plane to be updated. Moving on, how the developer writes the policy is in the form of these Copper policy programs. So the programmer says that I want to write a policy corresponding to a certain ACO, and they provide a context. What we mean by a context is a logical network path. As I showed earlier, in the microservice world, uh, a request can pass through several services, and therefore a sequence of services is important. And we think that directly using logical network path or the sequence of services for specifying policies is a great way of dealing with the problem of policy handlings. Specifically, the context looks something like this, which is kind of this happens before relation along with a wildcard so that we can support regex as well. So in this example that we have here, A star C implies that a request which goes from service A and then it can go through any number of intermediate services and finally ends up at C. We want to impose this policy on top of that. And what this policy is basically doing is it is checking how many of these requests were critical services, were critical requests. And the great thing with this kind of policy program is that we can support conditionals and assignments as well. And this is something which current service mesh frameworks have a hard time supporting. And this makes policy specification easy because we can use wildcards, we can use index expressions, which does not require the programmer to give this exact specific path that the request takes. It can be general enough. Now, so that was the second component. Moving on to the third component, which is the control plane. Let's compile some observations that we have until now. The first one is that you see these shaded policies, which are not really enforced. They're just there because the control plane does not know which service can talk to which other service. And if you think about it, that these two sidecars are, and actually these three sidecars are not really doing any processing. They're just there intercepting requests and not really doing anything about it. So not all sidecars are actually needed to enforce a policy. And we can remove these sidecars altogether while still achieving the same functionality. The second insight is that there are policies which can be enforced at multiple sidecars. So if we look at this policy P2 over here, this policy P2 was basically just adding the header from FE on all requests which go from front end to the back end. Because we know that there is no other service which is sending requests to back end, therefore we can actually move this policy around to the sidecar of back end as well, while achieving again the same functionality. And if we do that, then the sidecar at front end is also not needed. So in a case where we were already using 5 sidecars, we can achieve the same functionality by just having one. So this is our end goal. And how does the control plane get to this? Is the following. Given a policy P with a context, again the context to remind is the path which the request is taking and the path on which the policy is to be applied. If we have this context available, then there are exactly 2 places where this policy can be implemented. Either at the sender of the penultimate node, which is B in this case, or the receiving end of the ultimate node, which is C in this case. These are the places where we know that this request has traversed path A, B, and is going to C, or it has already traversed path A, B, and C. At any other place in the path, in the logical path, for example, if we were to implement it over here, we do not know whether this request is actually going to go from A, B to C, or will it end over B, or will it go somewhere else. And therefore, there are exactly 2 places where this policy can be enforced in the entire path. This gives the control plane an option of choosing whether to implement it over here or over here. So it gives exactly 2 options for every policy. But there is some problem over here. We said that we can move policies around from the sender to the receiver, but not all policies satisfy that requirement. There are some policies which are tied to a specific endpoint. For example, set deadline is a policy that you can only do at the sender. You cannot set a deadline when you have received something. You can only do that when you are sending something. And this is something which the data plane knows. The data plane knows which of its operations can be done on the outgoing requests and which of them can be done on the incoming requests. And that is exactly what we achieve in our spec programs via something that we call locality fields. And it's just a small piece of syntax which describes whether this action can be applied to outgoing requests or incoming requests. And this gives an additional information to the control plane as to where this policy can be implemented. By default, it assumes that the actions can be implemented either on the sender or on the receiver. But if this kind of a keyword is given, then it imposes a constraint for the control. Using all of this information, the control plane can then can use a variant of the set cover problem. It's an optimization problem, and it can use an optimizer to solve for the policy placement. I can go over more details, but in the interest of time, I'll just provide the high-level intuition over here. We can model this as an optimization problem and use an SMT solver. The constraints are the policy contexts or the paths. And remember that each policy can be implemented, can be enforced in one of two places, modulo the locality of policy actions, because some policy actions can only be done on the outgoing edges or on the incoming edges. And the optimization goal is to minimize the number of sidecars. And if we do this, then we can get the minimum number of sidecars needed to enforce policies, and therefore reducing unnecessary overheads of latency and CPU and memory usage. Putting it all together, with CopperWire, our goal is to redesign the entire service mesh stack, and this leads to more expressive policies as well as better performance. And there is no real trade-off between expressiveness and performance over here. So here is how the overall workflow looks like. The data plane vendors provide their functionalities in the form of spec programs, and each of these spec programs has a list of ACOs and actions supported by the data plane. This is a new abstraction that we introduced. This can be used by the developer directly to write policies, so they know which ACOs are supported and what actions are supported. Plus, they provide a context which makes it easy for them, and they don't have to break down their policy into small sub-policies. This context makes it easy and intuitive. All of this is submitted to the control plane, and taking in the application call graph, it can optimize for the placement. So in this case, we have like these 7 services, and we only for some set of policies, we only need 3 sidecars to implement it. So it can do optimal placements, plus it can also choose which data plane to use for each service. Overall, this gives a better performance, and it can also it is also easier for the developers to write their policies. I would just like to end with some future directions. The service mesh space is very interesting, and it has a bunch of very interesting problems. Here I tried to categorize the current challenges in 3 buckets: architecture, features, and applications. What we have tried to deal with in CopperWire is the performance overheads of the data plane, some optimizations and specification of the control plane, and a feature of policy upgrades. But there are still several other interesting things, and if any of you is interested, I'll be happy to talk more about it. With this, I would like to conclude my talk, and I can take some questions.
Thanks, Divyanshu, for this wonderful talk. Any questions? Yeah.
I think the room is on mute, so I cannot.
Hello, can you hear me now?
Yeah, I can hear you.
Yeah, hi.
Sorry, this is Devapam.
So one quick question that I have is, what I understood is that there is a learning curve for the developers, right? And different data plane vendors might come up with their own version of, the framework. So, what challenges do you foresee, and is there a way by which different vendors could come together and offer a uniform framework instead to reduce the learning curve?
Mhm. Yeah, so I think a standard API, people can come up with it, but there is a real mismatch on what each of these data planes provide. So just to go back to this, yeah. So actually, yeah. So to give a concrete example, there is a data frame called SVO, like Envoy, and then there is another data frame called Linkerd, which is a more lightweight version. The reason why people developed Linkerd was because Envoy was very heavy, it was very bulky. So they built something from scratch, which does not have a lot of features. It has very few features, but it is lightweight. Now, if you were to come up with a standard API for both of them, then it is likely that the API would either be too general or it would leave out some functionality. Therefore, it is probably better that each data plane gives their own uh, library that what is it that they can support. Plus, there is also this thing that when we have this makes the onboarding of data things much more easier. So if there is a new player who is not part of a gigantic organization and they want to develop their own data plane for service meshes, it becomes much more easier for them to specify what is it that they can support and to make use of and to reach out to actual clients instead of having to wait for some general control plane to uplift their functionality.
Okay, understood. I have another question, but
Yeah. You can go ahead.
Another question is you mentioned that these handlers would be continuously on, which means they would consume some CPU throughout. So at scale, what is the overall like, and do you see any performance impact at scale?
Sorry, I did not catch the last line. Do you mean that at scale what happens?
At scale, what's the CPU overhead, like the consumption of CPU?
Right. So I think let me go back to So this is the CPU usage graph that the numbers that we got, and this is not like at scale per se. It's just some benchmarks, some microservice benchmarks. And book info is really small. It's like 6 or 7 services. Boutique is like 12 services. Reservation is some 28 services. None of them actually reflect like how production level microservices look like. But as you can see, there is like an increasing trend, right? So as the microservice graph increases and you have more services, you also have more sidecars. And each of these sidecars has some performance and latency overheads, and plus resource overheads. So if you just take like CPU usage, uh, depending on what request rate you are operating at, it can be almost like 2x higher CPUs. So you might just need like twice as many machines to run your microservice application.
Okay, understood. Thank you.
Are there any other questions? Anybody who are online? Any questions? Okay.
Divyanshu, Saurabh this side.
Okay, yeah.
So I have a question. You mentioned about each container having its own sidecar, and by using this copper mesh, you try to optimize the number of sidecars, even the number of containers. So I was wondering whether copper this your new technique can also suppose there are multiple services which require a common type of functionality like distributing the traffic. So can multiple containers go ahead with the same sidecar?
Right. So that's a good point. And the way these service mesh layer has evolved is that earlier there used to be like a per node proxy. So all of the containers that you have on a single physical machine or a single node, they would just share one sidecar. And the problem with that was that it requires like some level of isolation, and there is also blast radius. So if something goes wrong with one of the policies, policies, then multiple services are impacted at the same time. So the reason why each service gets its own sidecar is because there is isolation, there is independent scaling. So if there is like too much traffic for one service, it does not impact any of the other services because each of them have their own sidecar or like have their own policy enforcement module. If it is shared, then it's very difficult to ensure isolation. So if there is like, let's say both of these two services share a sidecar and front end is getting way too many requests compared to the back end, then it will essentially throttle the back end service. And that's not something that you want. You want isolation. And therefore, that can be explored how to ensure isolation in shared sidecars. But the trend is that people are moving towards this per service sidecar.
Okay, good. Thank you.
Thanks for the question.
I think, is there any other question? Or maybe you can also connect with Divyanshu online over email. Thanks so much, Divyanshu. Thank you so much for sharing your insights with us. And
Thank you. Thanks a lot.
yeah, we'll get back to you sooner. If you guys can share your slides also, that would be great. If we can, is it okay if we can put it on the public domain?
Yeah, sure. I can share.
Yeah. Thanks so much, Divyanshu. So let's proceed with our next invited talk. Satadal, can you please check whether you can share your slides? Yes, we can see. Yeah, so we have with us Satadal Sengupta. Satadal is a fifth-year PhD student at Princeton University. He's advised by Professor Jennifer Exford. His research revolves around accurately measuring and improving the performance and security of the internet, especially by leveraging the high-speed programmable data plane. He'll be talking about how can video conferencing be made more measurable and performant. So thanks, Satadal, for accepting our invite. Over to you.
Thank you so much, Renko, for inviting me, and thank you all for gathering. Good morning to everyone joining from India. Good evening to people joining from the US, and it's very late here, so I hope I don't put you to sleep. Okay, all right. So the topic of the title of my talk is Zooming In, Enabling Measurement and Improving the Scalability of Video Conferencing. And the word Zoom is strategically placed in the title because I'm going to talk quite a bit about it in this talk. So this is joint work with Oliver, Ravi, and Jen at Princeton. So video conferencing has emerged as an essential application across most of the industries in the last few years. And this is no surprise, we all know about this. There are critical applications in education, healthcare, business, and so on. It has become very relevant in the research community where there has been a lot of research in improving encoding technologies, improving rate adaptation, congestion control for video conferencing, and so on. And it has become increasingly relevant for network operators, like say the Princeton IT department, because there is a going over the networks, and they need to make sure the quality of experience is really high for their users. So in this context, let me first begin with giving you a brief introduction to how video conferencing even works. So we can broadly divide this into 4 components. And the first, okay, so the first component can be called connection establishment, which is where there is a client somewhere in the world, like say me, who wants to start a call, and it indicates to a signaling server somewhere saying I want to start this particular video call. Then a bunch of other participants come in and they say they want to join the same video call, and the server establishes this connection, and they are all now allowed to talk to each other by this call. So in the second phase of this, the media is generated and prepared to be transported. And so what this means is that the client generates its video and audio, like I'm doing right now. There is an encoder in my system that would encode these media streams, and then packetize it, basically divide it up into packets such that it is ready to be sent over the network. And these packets then reach a server that is controlled by the application, like Zoom in this case, and this server is called the selective forwarding unit. And this component of video conferencing can be called media distribution, where the selective forwarding unit is basically replicating these media streams to the other participants in this call. So for you folks, for example. And this is happening in all directions, right? So all the participants in the call are basically streaming their media to each other. And the final phase is actually relevant after everything is working. It's great when it's working well, but what happens when there's congestion in the network? So if one of the participants faces congestion in their network, then what will happen is there has to be some sort of feedback mechanism so that the video quality on that end can be adjusted so that the experience is smoother instead of them just dropping out of the call. So with that in mind, let's think a little bit about what I want to achieve in this talk, right? So we have these two clients, let's say on two ends of the world, and they want to talk to each other via call. So what happens is the media stream emanated by the first participant will first go through the campus of the enterprise network, like say the Princeton network here. Then it will be transported over the wide area network to the video conferencing server infrastructure that I talked about before. And then eventually it will again be transmitted over the wide area network to the other participant on the other side of the world. And most of the past and ongoing innovation that has happened actually at the end host. For example, there's been innovation in encoding technologies, in rate adaptation, and so on that I mentioned before. But the perspective of network operators in terms of what can they measure, how deep can their insights be about the traffic that they're seeing in their networks, and also the perspective of the conferencing infrastructure. So what can Zoom servers do better has largely been overlooked. And so in this talk, I'm going to talk first about the campus, the perspective of the campus of the enterprise network operator, and then I'm going to touch briefly upon the improvement in performance of the video conferencing infrastructure itself a little bit. So with that in mind, let's start by empathizing with the network operator's pain a little bit. So video conferencing has a unique kind of workload, which is quite different from any other kind of services people use, like downloading, browsing, video streaming, and so on. Video conferencing is characterized by strict latency requirements, right? So what I'm seeing right now has to reach you almost immediately with very few milliseconds of latency. And also increasingly there is high scale because lots of people are starting to use video conferencing during peak hours and so on. And so, as I was mentioning before, if there is high end-to-end latency, then what you will experience is lag. So my voice will reach you later, you will not have a good experience. But even if the latency itself is low, if it is highly variable, and therefore you have high jitter, you will have these experiences where you will receive broken audio or video. We have all experienced this, and we know that it can be super annoying. And so this kind of low quality of experience leads to disgruntled users, which means they will make angry calls to the IT department, right? And so the IT department, the operators working there, needs to measure the traffic somehow to know what is going on, to troubleshoot these issues. But it's not easy. And the point I want to make here is that it is really hard for these operators as well as researchers to really extract useful metrics from all the traffic that they see on their networks. And why is it hard? Well, first, quality or performance metrics are actually not directly visible from the traffic. So it's not just a matter of capturing a few packets on your network, opening it up on Wireshark, and looking at it and then saying, oh, this is the reason there's an issue. Because first of all, it's not trivial to figure out which packets belong to which application. Then you don't know which of those packets belong to what meeting, what participants they're coming from, and in some cases, these packets headers are even not in a standard format. So you can't really say anything beyond looking at aggregate packet rates. Secondly, some of these applications like Zoom, for example, does provide some metrics like bitrate and so on to help with diagnosis, but really these are only useful in the small scale. So they present this to enterprise users via the Zoom API, but you get them at a very low granularity, like 1 measurement per second, and these are only useful if you're looking at a small scale controlled experiment, but does not really scale well and does not give us enough insights to troubleshoot finer grained issues, like when someone is repeatedly facing a glitch but is seeing consistent performance averaged over a long time. And also the scale can be daunting. So in a campus trace that we recorded from just a subset of our Princeton campus, we found that there's an average of 43,000 packets per second, and it can go up to 100,000 packets per second during peak times. So what we really want to do here in this part of the talk is help the network operator gain deeper insights into the video conferencing traffic that they are seeing in the network. Now, let me give you an example of how just looking at aggregate data rates can be really misleading. So a lot of previous work has actually tried to do this. So let's say you're looking at the aggregate data rate of a particular media stream over Zoom, and you see this dip suddenly over time. You want to know what happened here. Like, was there a network congestion? Is the network really bad at that point? Well, maybe not. So consider this example where two people are basically talking to each other, and you really don't know how to distinguish between the traffic emanating from each one. You're just looking at the aggregate data rate, right? So let's just say the blue participant disconnects. The red participant disconnects from the call at some point. So you will see this sudden dip in aggregate data rate, but you have no way to tell whether it happened because of network or because of something else, because you don't know what is actually going on in the meeting. Consider a second example where the red participant has not actually said bye, but has changed their mode to the thumbnail view that we are used to for Zoom. And we would see a similar effect in the aggregate data. So what I'm trying to say here basically is that unless we have more information about what is actually going on inside these packets, we cannot reason about the semantics of a call. So we need to dig deeper to extract meaningful metrics like latency, jitter, loss and retransmissions, out-of-order packets, the frame rate and sizes of individual frames, the media bitrate, and most importantly, maybe the meeting composition, which means how many participants are in the meeting, how many of them are emanating video or audio or screen sharing and so on, when does someone leave, when does someone join, and so on and so forth. So in this work that we published in IMC, we wanted to have this goal in mind, which is measuring and analyzing the performance of video conferencing sessions in the wild, but with certain properties. So we only want to do this from passively collected packets. So we are not doing any active measurements. These are real packets from real users. We want to do these measurements without any sort of end-host control. So this is completely in the network, and we want to scale this up to actually production scale networks. We choose Zoom for this study because it is widely used in general, but also at Princeton. And also it is particularly challenging because Zoom has a proprietary packet format which was actually undocumented before our work was published. So why is it challenging to really measure video conferencing? Well, part of the reason is actually that video conferencing itself is complex to understand and is challenging. So video conferencing can use different kinds of architectures. So there can be cases where there is a peer-to-peer network of the different clients who are talking to each other. So you have to identify these clients separately in that context. Or they can go via an SFU, as I showed even an example before. So the strategy for identifying these packets, these media streams, will be different in each case. Second, the traffic, at least reportedly, is encrypted and and therefore it's very hard to know what is actually going on. So we are not even sure if certain parts are in the clear or encrypted, because sometimes there can be proprietary headers. So we need some way to reason about that. And thirdly, when we think about meeting composition, video conferencing actually has multiple layers, right? So you have a meeting, you have participants within that. Within each participant, you have different media, like audio and video. Then you can actually have different sub streams within that. And then those are divided up into frames, and then finally you have packets. So you have to reason about the entire hierarchy of these components within video conferencing. So we ask these particular questions. First, we ask how do we reliably detect all of the Zoom traffic given these different architectures that can be used. Second, what is the Zoom's packet form? What is Zoom's packet format, and what information can we extract from these packets because they look encrypted on first look? And then how do we group packets belonging together such that we have better insights into which of them belong in the same meeting, and what information can they give us about a particular meeting? So, talking about the first part very briefly, for server-based meetings, it's actually pretty easy to find them. Zoom publishes a list of IP addresses and port numbers for their servers, so we use that to detect that. For peer-to-peer meetings, it's actually quite complex, and if you are interested, I'll refer to the paper, but essentially we rely on our understanding of stun packets and their exchange, which needs to happen before the peer-to-peer connection establishment. But I must note here that peer-to-peer is becoming increasingly rare, and Zoom only uses it for two-person calls, but that too under specific circumstances. Secondly, we want to infer the header format. And if you just opened up a Zoom packet before and looked at its data, it would look like what you see on the right-hand side. It's just a bunch of bits, something that you cannot reason about beyond the standard UDP header. So we wondered, are there unencrypted parts in Zoom's media packets? It looks like it contains information, but is that really true? And if so, if there are encrypted parts, are there then patterns that we could use to then find these header fields? So we did this entropy analysis, where what we did was we took subsets of bits from the UDP payload and we plotted them across consecutive packets. So our reasoning was that if you see these bits having, these sets of bits having random values across multiple packets, then we have probably hit a part of the packet that is encrypted, part of the payload that is encrypted. But if you see something that has these consistent values or horizontal lines, then they're probably identifiers or bit fields. And if they are increasing like this, or they have diagonal lines, then they're probably sequence numbers or timestamps, so forth and so on. So we now use these insights to actually dig deeper into the UDP payload, and we uncover the following. So after the UDP header, Zoom actually uses this SFU encapsulation layer. We named it such because it seemed appropriate. So it has the type, which really refers to whether it's media or not, the sequence number and direction, whether it's from the server or to the client, and so on. The next layer is the media encapsulation layer, which tells you what kind of stream this is it video, audio, screen share, etc. Sequence numbers, timestamp, frame number, and also tells you how many packets are in this particular frame. Then there is the RTP header or the RTCP header, and this is a standard protocol that is used in a lot of real-time applications, including video conferencing. So we had a suspicion that RTP might be used inside Zoom, but we did not know where to look for it. And after this analysis, we were actually able to find it. And then eventually they have the media header, where there are some identifiers and some more information. And eventually you have the media payload, which is then actually encrypted. So we uncovered all of this, and we wrote a Wireshark plugin for Zoom that has been released as part of the paper artifacts. So you can download this and open up your own Zoom packets and see inside them what's going on. The third thing that I talked about is grouping packets by meeting. So as I was saying before, the knowledge about individual streams is not actually sufficient for example, to do latency or jitter measurements and so on. We need to have more context. We need to know who all are talking, when are they joining and leaving, and so on and so forth. So for this, what we did was we looked at streams that were leaving and entering our Zoom campus, our campus network, because we had a monitor at the edge of the campus network. And what we did was we did this two-step process where we looked at outgoing streams that also had a matching incoming stream. And so we knew that, well, when someone is emanating a stream, it is coming back to some other client within the same network, and therefore they must be in the same call. And we use some more heuristics based on timestamps and so on to then cluster sort of these media streams into one particular meeting. And what this let us also do is compute something like round trip time for RTP packets, because now we have packets that are leaving and packets that are coming back in for the exact same meeting, exact same media stream. So armed with this, we can now reason better about these metrics that we care about. So here's an example of what we can do with this information. So let's say there are two participants. Participant 1 is sharing their audio and video, and participant 2 is sharing audio, video as well as screen share. So first, to begin with, people could only look at all the packets, all the UDP packets from this meeting, and have no deeper insight into it. But now we can tell which of these packets belong to participant 1, which of these packets belong to participant 2. But that's just scratching the surface, right? So now we can dig deeper and say, well, participant 1 is actually sending audio and video during these particular timings. So you can see in this example, participant 1 stopped sharing their audio for some time because they were screen sharing during that exact point. Because participant 2 was screen sharing because during that exact point in time, and so on. And not only that, we were actually able to even figure out when someone was speaking or not speaking from their audio stream, which was very interesting and potentially a risk to privacy as well. So now that we have all of this information, we can confirm that we can compute the media bitrate, frame size, latency, jitter, and loss-related statistics, like transmission, autocorder, and so on, just from looking at the header. Some of these are actually available via the Zoom SDK, like frame rate, latency, and jitter. So we were actually able to go ahead and validate that what we measure is actually what Zoom is also reporting. So I'm going to briefly go over that and show here that we actually did some controlled experiments. I'm not going to go into details, but you can see that the blue curve is actually what we measure, and the red dots is what Zoom reports. And we pretty much exactly match what Zoom reports, except ours is better because we report up to 30 samples per second, whereas for Zoom, they just report 1 sample per second. And in some cases, that means we detect some dips that Zoom is not able to report. In case of latency, we perform well again, and our observations match Zoom's observations, but again, we are more finely tuned, and you can see here that Zoom actually even aggressively averages its latency reports, meaning that sometimes it can tell you it is performing better than it actually is. And also the latency reports are slightly off in time, as in they report incidents slightly later, higher latency slightly later. One curious thing happened is that jitter did not actually add up. So interestingly enough, Zoom reports close to 0 jitter for this exact stream, and you can see that the latency has changed quite a bit in the graph on the top, and so you would expect that there will be some impact on jitter. So 0 just does not make sense, and indeed our reporting shows that the jitter is also roughly correspondent with the variations in latency, which makes more sense. So our methods basically uncover some ways in which we improve quite a bit on what Zoom is reporting and so on. So one interesting sort of observation from all of this is that we found that Zoom actually tries to encode video at 28 frames per second. That's the red arrow that you see on the graph to your right. So that's their target frame rate. But we also see that 75% of the samples that we collect show a frame rate that is less than 20 frames per second. Does that really mean our network is really that bad? Because 75% is a lot, right? And it's not the case. So what happens is that a lot of times things like thumbnail mode is being activated, someone is screen sharing, and so on. And in these cases, along with reducing the bit rate of the actual video, Zoom also reduces the frame rate and cuts it down to half. So it targets 14 FPS instead of 28 FPS. And this is something we wouldn't know if we hadn't done these measurements. And also, interestingly enough, we see that for screen share, Zoom actually uses a lower frame rate. And for 15% or so, the frame rate is actually 0, meaning that if I am, like in this case, when I'm presenting a particular slide to you, I'm not changing that slide for a while, right? So there's no need to actually change the frame at all. So, and that is reflected in the frame rate. All right, so I'll come back to my roadmap, and we spoke about the vantage point, the perspective of the network operators quite a bit, and I'm going to touch upon briefly on the conferencing infrastructure. So I talked before about the selective forwarding unit and what it does. So to remind you, how it basically replicates media streams. And essentially what this means is that it handles a high volume of traffic in the CPU, right? And it replicates individual media streams to multiple participants. So there's a 1 to n-1 fan-out, meaning if there are n participants, one is sending and it's going to everybody else. And then this is happening per participant. So one interesting thing to note here is that the work of the SFU is inherently quadratic, right? It scales quadratically given the number of participants. So we looked at 10 days worth of data from the Princeton campus, and we saw how this sort of shapes up in reality. So in this plot, the curve that you see in gray, the dotted line, is actually what would happen if everybody in all meetings was always sharing their video and audio at all times. But obviously, as the number of meeting participants increase, some of them will stop their video or mute their audio and so on. So you don't exactly see quadratic, but you see that the scale is pretty steep. And so that's something that we need to worry about. So just to give you a concrete example, let's say there's a meeting with 7 participants and an 8th one joins that particular meeting. Now, when there were 7 participants, there would be 84 streams among them if they were all sharing video and audio at the same time, and it would immediately jump to 112 when the 8th one joins. And increases like this can easily exceed the max capacity of the server that is handling these media streams. So an application provider might want to mitigate this, but what can they do? So one, they can be reactive, right? So when the server capacity is exceeded, they can migrate that meeting to another server. But obviously this comes with high overhead. Or they can be proactive. They can over-provision their servers. But keep in mind that meeting sizes are dynamic and can actually be hard to predict. So you will have to really massively over-provision to handle all kinds of cases that might happen, and so you might be wasting a lot of your resource. So we look deeper into what does the SFU actually do to understand better how can we help it. And so we basically figured that it is copying packets to multiple participants from media stream. So in this image, you can see that if there is a 30 FPS stream, it is, and there are a 30 FPS stream coming in, and there are 3 other recipients that it goes to, then it is basically copying these packets 3 times and sending them over the network. Also, in the third case, I must say that if you see it's cut down to 15 FPS, it just means it has dropped some of the intermediate packets. It has halved the rate by dropping some of the packets. That's all that it is basically doing. And why it is able to do that, why is it able to drop packets and reduce frames and still have the whole thing work, is because frames and resolutions actually align with packet boundaries. So if you know which exact packets constitute a particular frame, you can drop all of those packets and then you'll basically lose a frame, and things can go work well if the encoding takes care of that. Similarly for resolution, if you use something called scalable video coding, I'm not going to go into details, but essentially, as long as the packet headers contain this information, the SFU can do all of this. And so the rate adaptation in this case is happening by dropping packets, as I was mentioning. So here is our key insight in this part of the work. This work that the SFU is doing in the CPU is very akin to traditional packet processing. And the replication, the copying of packets is similar to network multicasting, right? And also packet dropping is something that switches or any kind of network device is familiar with. So can we then use this insight to offload this kind of work to a more specialized environment rather than have this be in the user space? And so we talk about offloading SFU packet processing, so we can use programmable platforms designed for efficient packet processing and replication such as ABPF, SmartNICs, programmable switches, and so on. These switches, incidentally, are inside sometimes the same data centers where these SFUs are, so we don't necessarily need to introduce new hardware. We can leverage some of the hardware that is already present. These ensure that packet processing per packet is fast and predictable, which helps in reduce latency and jitter, but probably most importantly, the bandwidth for these devices is orders of magnitude higher, and it really lowers cost of packet processing. But why is this hard to do? It's hard because all SFU functionality cannot be offloaded. There are complex steps like signaling and rate adaptation that cannot just be handled by a simple packet forwarding device. And also, it is not obvious where to draw the distinction between the control plane and the data plane. So which packet should be handled in the control plane and which in the data plane is a non-trivial question to answer. Also, video conferencing was not designed with the data plane in mind, right? It was built as a monolith. So it's really hard to figure out how to really offload some of this to the data plane. And as we saw before, packet headers contain rich application semantics. They contain information about participants, media streams, so on. So the data plane actually needs to be aware of those things in order to make the right decisions. So I'll sort of end by talking about the opportunities in this space and first give you a glimpse of some early results that we have. So we made the point that offloading this work can vastly improve scale and therefore lower cost of operation. So if you assume 3-party calls at 640p video per participant and audio as well, the Intel Tofino, if you use it, can actually serve between 100 to 300 times more meetings than a typical 10 to 40 Gbps server can. And actually, we did the measurements and we figured that 97% of the packets that are served by the SFU can be handled directly in the data plane. Only the rest of the 3% and less than that actually is handed over to the control plane, which then reduces the load on the control plane a lot. And we can, this architecture can actually support up to 700,000 concurrent meetings, which is quite a bit higher than what is supported today. Also, if we are able to do this, then we can have hierarchical implementations. So you can have one control plane that is sitting somewhere in a data center and potentially multiple data planes. And these data planes can actually be close to clusters of recipients. So let's say there's a bunch of people in Princeton talking to a bunch of people in Stanford, and if you have one switch in Princeton and Stanford, they can handle their local traffic much more efficiently, while only sometimes sending some packets to the control plane for higher level processing. And this will reduce reaction time to network events significantly. Congestion control can happen locally, and so on. And also, this whole architecture can open up innovation due to its modular nature. So maybe there are things that can be done that we haven't even thought about yet. And so that includes things like custom rate evaluation algorithms and so on. So I'll bring us back to this roadmap. We talked about the vantage point of the enterprise network, the operator of that network, and we talked about how to improve the video conferencing infrastructure. And with that, I will finish my talk. Thank you.